Welcome to Molar Mass by Freezing Point Depression. This is for Chemistry 104L. First, where do you find the information that you're going to need to perform this lab? You need to go to Blackboard. So what I'm going to do first is share that screen. And let's see, here we go. Now this is the way you get to Blackboard. You probably already know that, I would hope by now. So let me log in. Find your course. And let's make it look like a student's Blackboard. There we go. So start here. Typical, that's the way I do all my Blackboard courses. Start here. Lab exercise. All right. And here's the first lab, molecular weight by freezing point depression. Molecular weight and molar mass, for our purposes, are synonymous terms. So when you open that folder, you'll find the molar mass by freezing point depression. This is your hard copy for the lab. Then you'll need this other one, the data. So let me click this one and just show you what it looks like. All right, there we go. All right, so that's what it looks like. You'll notice that there's a pre-lab question. All right, so you have to do that one. And then there's procedure, activity 1, activity 2, and I'll explain what those activities are about later. Then you'll have some laboratory questions that you do after the lab. You have to put them into your formal report. And then there's some, hopefully, helpful information in the appendix, which gives you a description of how to do molar mass by freezing point depression. Actually, this appendix has boiling point elevation, which I'll allude to later. But if you focus on this side over here, freezing point depression, and use that information that's given, you'll see how they work through the problem. And I'm going to do this in this presentation also. But there you have an alternative version that you can study if you wish. So let's go back to here, and this is what the data will look like. Okay, so there you have a table. Notice there's a table here on the left for the pure lauric acid, and that'll mean something more to you later once we've gone through the lab. And the lauric acid plus benzoic acid is part 2. And I've conveniently identified in this data set what is the freezing point for the pure lauric acid down here in red, and what is the freezing point for the solution of lauric acid and benzoic acid down here in red. Okay. Then here's the mass of your lauric acid in grams, and the benzoic acid mass. And here's the accepted value for your benzoic acid. And here is the K value for lauric acid. And that'll mean more also as we proceed through this demonstration. I see we're missing something here. It didn't come through. All right, that's okay. In that blue square was supposed to be the formula for freezing point depression. I'll give that to you in the body of this presentation. So you just fill it in or write it down somewhere. It's also in the method. There are a number of places where you can find that information. But this data, you'll want to graph that, right? Temperature on the x-axis, temperature on the y-axis, time on the x-axis will give you a curve, and same thing for the solution. Okay, so that's all you need from the from Blackboard. This also shows you your Dropbox, right? So when you finish your formal report, that's where you put it. You just click on that, it opens up, and there's a place for you to attach your formal report and send it to me. It'll pop up in my grade book, and I'll see that you've submitted it, and then the ball will be in my court, as they say. Okay, so let's exit that for now. And let's see, some other stuff that I was doing. So let's stop the share. Okay. I'm going to pause for just a second. Okay. Normally I like to have cats around me when I'm working, but not when I'm making a video. This one was getting in the way, so he's gone. All right, now let's get to the the meat of the topic. That's where you find all your information in Blackboard. Now, let's talk about the theory behind the molar mass by freezing point depression. Best way to do that is look at the title. The title gives you lots of information. And if we break it down, molar mass, that should be old news for you, since you've already had the first semester general chemistry. You'll know that molar mass, notice that I always abbreviate that MW for molecular weight. That's just because I'm old. And that's the way we used to do it. So molar mass is equal to the mass of a mole of the compound. So that means that up here, you'll have mass in grams. Down here, you'll have moles. Okay? So the mass is the easy part. You've weighed it out. The mass we're interested in this instance is the solute, or benzoic acid. Benzoic acid will be in the neighborhood of a gram, and that data file that I showed you in Blackboard is where you find that information. So that'll be the mass. Now we have to find out how many moles does that mass represent. To do that, we're going to use a colligative property. Okay, so what's a colligative property? Well, we haven't covered that yet. At this point, that's in chapter 11. In fact, 11, section 5, I believe it is, discusses colligative properties. And there are 4 of them. Actually, there are 4 of them that we're the only 4 I know of. One, wait a minute, before I do that, what is a colligative property? A colligative property is the property of a substance that, actually, it's a property of a solution that depends only on the number of particles of the solute and not on their identity. So it doesn't matter what compound it is. All we're concerned with is the number of moles of that compound in the solution of whatever solvent it happens to be. And the only condition is that the solute is soluble in the solvent, obviously. Otherwise, it just won't work, right? There's no colligative property for oil and water. Okay, so now that we know what a colligative property is, there are 4 of them that are explained in your text. One is boiling point elevation. So what does that mean? That means the boiling point of the pure substance, the pure solvent, is a value. And if you add some solute to that solvent, it tends to elevate the boiling point of the solvent. Okay? The one we're interested in is freezing point depression. So we'll have a freezing point for our solvent, which in this case is lauric acid, which is a fatty acid. And when we add a known amount, a mass of solute to that solvent, and our solute is benzoic acid, when we add a certain amount, we get a depression in the freezing point. Okay? So we'll come back to that in a minute. What's another one? Osmotic pressure. It will take too long to describe osmotic pressure here, so I'll save that for the lecture, and then it'll become clearer. Also this one, vapor pressure. And vapor pressure is governed by Raoult's law. So that will take some time also, and we'll do that during the lecture. The one we want to focus on is this one, freezing point depression. Okay, so now that I've run out of room, let's erase these, and we'll come back to freezing point depression. And freezing point depression is going to allow us to determine how many moles of that solute we have in the solution. We know how much mass it is because we weighed it. Right? You have to imagine that you weighed it, hands-on in the lab. And then by this colligative property, we will determine how many moles that represents. Okay, so in order to do that, we need freezing point depression, right? Freezing point depression. Well, there it is right there. Why write it again? Freezing point depression. And that is represented by a delta T, a change in temperature. Now, the pure substance will have a freezing point, and the solution will have a freezing point that is lower than that. So the freezing point is depressed. But the delta T that we're interested in is the absolute value of that depression. Right? So we only care about the magnitude, the number. We don't care about the sign. You should get a negative sign if you follow calculation protocol, where that delta T would be final minus initial, right? So if the initial temperature is higher than the final temperature, you get a negative number. But we don't want the negative. We only want the absolute value, just the number itself. Okay? So the formula that governs this property is equal to the concentration of the solute in the solution, and I'll describe what that M means in just a minute, times a proportionality constant. Right? That K. Now let's go to the K first. The K is characteristic of and experimentally determined for the solvent. The lauric acid is our solvent. Right? So this K is unique to the lauric acid. It doesn't matter what we put in the lauric acid as long as it dissolves, and it will depress the freezing point. But if we use something else besides lauric acid, the K will be different. Right? So in your method, and I'll write it up here, that K is equal to 3.90. I'm going to put the units in there in just a minute. First, we want to say, what does M mean? M is an expression of concentration of the solute in the solution. Right? So we know about molarity, right? Molarity is moles per unit volume, which in this case is liters, right? Okay, there's the problem. If we try to use molarity in this expression, where the temperature is changing, we want the temperature to change. What happens to the value of M? It changes with temperature because we have volume here. What happens to the volume of a liquid when you change the temperature? The volume changes. We don't want that. We want the concentration to be fixed for the entire experiment. So we need a different expression. And we've got one. A little m. This is molarity. Right? This is molality. Okay? You still have moles in the numerator, but in the denominator, you have mass instead of volume. And as the temperature changes, the mass does not change. That's what we want. So in the denominator, we have mass, and it's in the units of kilograms. Okay? So this is moles of the solute per kilogram solvent. Okay? The solute in our case is lauric acid. The kilograms of solvent is, oh, I got that backwards. Correction, moles of solute is benzoic acid. Kilograms of solvent is lauric acid. Okay. So now we have the molality, and we have the units of measure, moles per kilogram. Notice the difference. This liter is the total volume of the solution. That includes both the solute and the solvent. But in molality, the denominator is in kilograms of solvent only. Okay. So be careful when you're looking at the amount of solvent, because it's going to be in the neighborhood of 8 grams, right? Something like that. That's not kilograms, is it? No. It has to be kilograms to be molality. So how do you make kilograms out of grams? It's real simple. Just multiply it by 10 to the minus third. So 8 grams is 8 times 10 to the minus third kilograms. Easy. Okay. Remember that one when you start to do your calculations. Now, it may not be exactly 8 grams. Look at your data sheet and find the exact value. Then multiply it times 10 to the minus third when you need to use it. Okay? All right. So let's make some more room and look at our units of measure. All right. So if delta T is degrees centigrade, okay, and molality is moles per kilogram, what units do we need for this value in order to give us degrees centigrade? We have to cancel moles, cancel kilograms, and leave us with degrees centigrade. So that makes it easy, right? Degrees centigrade has to be in the numerator. Moles has to be in the denominator. And kilograms has to be in the numerator, right? So the units on our constant, 3.9 in this case, are degrees C kilograms per mole. Okay? Now, if you ever do this experiment with a different solvent, you'll have a different value for K. And if you try to look that up, that value, try to look that value up in a reference manual, it may not have the units listed that way. It's very possible that the units instead of like that will be degrees C per molal. Okay? So notice molal is in the denominator. That means it's the inverse of molal. See this part? Kilograms divided by moles is the inverse of moles divided by kilogram, which is molal. So when you start to do your calculations, if you want to be sure that you cancel correctly, just change this to moles in the denominator, kilograms in the numerator, and put it in your formula, and you'll be fine. That's why I like to write it like this rather than like that, because this way you have the proper cancellations. Okay, that's just a word of warning if you ever look this up on your own. Okay, so there's our formula. This is a constant. We're going to determine this value by our 2 experiments, one with the pure lauric acid and one with the solution with our benzoic acid. And the difference of those freezing points will give us this value. So that means you have a value here, one unknown. And what have I always said? Any equation with one unknown, you can solve. So we're going to solve for molality. All right. So what do we do with molality? Once we have a value for molality, this will be moles of benzoic acid per kilogram lauric acid, right? So what if we know how much lauric acid is in there? If we multiply this times the kilograms of lauric acid, we get moles of benzoic acid, don't we? So we just go back up to our molecular weight, where we know the mass of lauric acid and the moles of lauric acid. We got the mass already. We just calculated the moles, plug it in, there's your answer. All right. All right, so I need to show, let's see. Yeah, that's good. I'm reading my script. my outline. So now I need to show you how the experiment progresses. Since you can't actually go in the lab and do it yourself, I need to explain it in sufficient detail. And I need more room, so let me do this. So I have plenty of room. There we go. All right. So first thing you need to know is what materials are you going to need to do the lab? All right, materials. There we go. Materials. All right. We need a tube, a test tube, to hold the materials that we're going to melt and then refreeze to measure their temperatures. Right? So we need a tube. So first thing we need is a test tube. We only need one, and the one that the data that we used to collect the data was a fairly big one. And I believe it's 25 by 200 millimeters. Right. So 25 millimeters is about an inch, and 200 milliliters is about 10 inches. It's a big tube. What else do we need? Well, we need our lauric acid. Right? Lauric acid is a fatty acid, and we've all got some in our bodies. They're in a compound with glycerol to make a true fatty acid. Then we need, that's the solvent. All right. Now we need our solute, which is benzoic acid. Okay, that's our solute. Okay. Then we need thermometer. All right. We need a water bath. How are we going to make our water bath? Well, we're going to use a 600 milliliter beaker with distilled water in it. Okay. Plus water. Okay. Then we're going to need something to heat that water up, which would be a hot plate. Now, when you read the method, it might call for Bunsen burner, right? But we actually used a hot plate. It's safer. And we need a ring stand. Since you've had first semester chemistry, you know what a ring stand is. And then to that ring stand, we attach a clamp that's adjustable up and down, plus it has adjustable jaws on it to hold the tube. Right? So we have a clamp. Okay? Now, we need some more stuff and we've run out of room. Right? So I have to go back up to the top and make room. Right, so number 9 is we need a spatula. You know what a spatula is, right? They come in different shapes. Some are, let's see, do I have one like that? Yep. There's a spatula, right? Or here's a different type of spatula. It's got a fancy name called a spoonula, right? Or if you're dishing out really small amounts, there's a small spatula. But we need a spatula. Why? Well, we're going to be measuring, we're going to be weighing our solvent and solute on an analytical balance. Right? So we need the balance, and we need weigh boats. You've seen the weigh boats that we use. They're kind of square, right? Made out of plastic, and you just set them on the balance, and you hit the 0 button to tare it, T-A-R-E, and then you start adding your substance to measure the mass. This analytical balance that we used will weigh to 4 decimal places of a gram, right? So it's extremely accurate. Let's see. Now, it's probably a good idea to have some paper towels for spills. And what else? Safety equipment, goggles, and what else do we normally need? Well, the goggles are provided by the lab, unless you have your own, and definitely the gloves. We use nitrile gloves. No latex gloves, so you don't have to worry about allergies. Okay, and you'll have your lab coat. We don't provide that. You have to have that. Okay, so that's everything that you'll need to do the lab. Now let's look at what you do with everything to conduct the lab. And remember, these steps that I'm showing you, when you write your formal report, you write the report as if you were there. And you don't say, we did this and we did that. You say, this was done. Third person. Passive. Past tense. Right? And you take a look at the rubric that I use to grade your formal reports, and you'll see there's a line item there, a category that covers that. If I don't see third person passive past tense, then you get graded down for it. If you regurgitate the procedure that's in your hard copy, then you get 0 points. Okay. So, and rather than explain what third person passive past tense is, just take that sample report that I gave you at the very beginning of the course, look at it, read the procedure, and you'll see what I mean by third person passive past tense. First person, I. Second person, you. Third person, he, she, it. So you say it or something by name. In other words, um, lauric acid, approximately 8 grams of lauric acid was weighed on the analytical balance. That's third person passive past tense. The exact values do not go in the procedure. The exact values go in the part of the report that includes the data, right? And we talked about that at the introduction to 102 and 104, our first day. I gave you explicit instructions as to what I'm looking for, the various sections of a formal lab report, and data is one of them. You don't put data in your procedures. You can say approximately to give the reader some idea as to what you're going to be measuring, but the exact values go in the data section, right? And that's why I gave you that example. So there are no excuses. You can see how it's done properly and imitate it. Okay, those are materials. All right, materials. Now, what do we do with them? All right, steps of the procedure. All right, it's going to come in 2 experiments that are virtually identical, except for one is pure lauric acid and 2 is the solution with benzoic acid included. Right? So I'll describe the pure one, and then you just repeat it for the solution. All right, so we take that tube. We actually take the lauric acid, weigh out approximately 8 grams of lauric acid. On our analytical balance, we get an exact value, which is in the data set, 8.0 something something grams. And that goes into, let's see, our tube. Right? There's our tube. And down here is our lauric acid. It's a solid. It's a flaky or granular solid at this point because it's at room temperature. We've waited, we know what the mass is, and we put it in there. All right? Now where does it go? Well, we have a clamp around it, right? We have a clamp. It goes over here to our ring stand. There's our ring stand and our clamp holding our tube. Now we have a hot plate. Okay. And we have a beaker. There's our beaker with water. That's it. Pure water, but the water is boiling. Right? So at our altitude, it's probably, I don't know, 97 or 98 degrees. It's definitely hot enough. And we submerge the lauric acid in the hot water and let it melt. One thing that I did forget to tell you. One other thing that we use one of the materials is a, we call it a powder funnel. powder funnel is, well, you know what funnels we've used before. They have a very narrow stem. A powder funnel has a wide stem so that you can pour solids through it. So we use a powder funnel. A powder funnel when we add our lauric acid in there. Why? So that we get as much of it as possible in the bottom. If you don't have lauric acid below the water line and it's heating up, then it'll never turn into a liquid and you have a source of error, right? So there's one possible source of error. You don't get all of your material in the bottom. So add that to your list, powder funnel. Okay, after the substance is added, then you submerge it in the boiling water and heat it till it melts. And you want to exceed 60 degrees centigrade. Say go up to 70, 75 degrees. Let's just say for the purpose of this method, go to 80 degrees, right? Heat it up until the temperature is 80 degrees. How do you know it's 80 degrees, right? Well, you take the powder funnel out and you put a thermometer in it. Right? There's your thermometer. It has to be submerged in the material or you won't know what the temperature is. Now, when it reaches 80 degrees, you loosen the clamp, raise your tube out of the water, and move it to the side. Why do we do that? Because if you don't get it away from the heat source, it's not going to cool down, right? So you just rotate it out of the way, away from the heat source, and then it starts to cool down. And you watch the temperature. Now, when the temperature reaches 60 degrees, you start recording time. That's time zero. Every 30 seconds, take another reading. So if you were in the lab, your partner would be, so one of your partners would be on the stopwatch, and just let the stopwatch run. Start it at 60 degrees. Write that down. Somebody writes it down. Somebody reads the thermometer. Somebody watches the clock. So you have 3 people in your group. At 30 seconds, the one watching the stopwatch says time, but they don't stop the watch. Let it keep running because you're doing this every 30 seconds and you're not stopping. Exactly 30 seconds each time. So at 30 seconds, your clock watcher says time, person reading the thermometer reads the temperature and shouts out the value, and then the recorder writes it in their lab notebook. And you do that every 30 seconds. And it's going to gradually get cooler, cooler, cooler. And at some point, you're going to notice that liquid, you start to see little crystals form of the lauric acid. Now, what you don't want to do is don't be fooled by crystals forming around the top of the solution. Let's blow it up. So there's your tube, and you have the lauric acid in the bottom. It's a liquid. Now, if you start to see crystals forming here and here around the edge, don't be fooled, because those are not at the temperature of the body, right? Your thermometer is still here. And you're measuring the temperature of the mass. These crystals formed at a lower temperature that you have not measured. So you want to look for the crystals in here, in the body of the liquid. So you're going to be constantly stirring. And it's okay to use the thermometer to stir as long as you're not too violent. Just keep it moving, okay? So you're looking for crystals forming in here. When you start to see crystals forming in here, the one that's observing it says something like crystals or freezing point. And the person that is recording it makes a mark at that temperature. Now, if that occurs between, it's not on the 30 seconds, then you read the temperature and say crystals and give them the exact temperature. So then the person that's taking the measurement, the person that's reading the stopwatch can make an insertion point between a 30-second interval so you know exactly when. But your data set that I showed you in Blackboard has the values recorded. I think one of them is whole degrees centigrade and one of them is, there was a half a degree. These thermometers are marked in degrees centigrade. So if you want to estimate, you have to estimate between. Remember when we talked about certain numbers, certain digits, and uncertain digits in a number? The uncertain digit is the very last one that you estimate. Right? So you want to estimate a last digit somewhere between those two. If it's right on the line, then your last estimate is 0.0. Okay. So that's what you're looking for, those crystals. And then you'll keep measuring the temperature as it goes, and it'll eventually solidify. But the data set is recorded in such a way that you notice the temperature dropping over time as the time proceeds, and then it flattens out. Right? Once you reach the freezing point of a liquid, when the solid and liquid are there together in the container, the freezing point stops. Now, you're going to graph this data, right? I want to see graphs. I want to see graphs of this one, see graphs of the solution. It's not as clear cut, but you can see it in the data set when you see the freezing point. Beyond the freezing point, the temperature doesn't change. Right? That's characteristic of all materials. When you have a solid and the liquid of the material together, during a phase change, the temperature does not change. It's like ice cubes in water. Stir them around. If you still have ice cubes in there, you're at the freezing point of water, whatever that temperature is. Okay. So that's how the data was acquired. So for experiment 2, we'll put the powder, we'll take this tube, put it back in the boiling water, and melt the lauric acid again. And while it's doing that, you go measure out 1 gram of benzoic acid, approximately 1 gram. And then when you measure it, you get the exact value, 1 point something something, with 4 digits, 4 decimal points. And record that. And then you come over here with your powder funnel and pour that in and melt them together. They have to be completely melted and dissolved in one another before you can proceed. And then you proceed exactly the same way as before. Raise the temperature, then pull it out, let it cool, start reading the temperature. And you'll find that with the solution, You won't see crystals at the previous freezing point. It will be a lower temperature, 4 or 5 degrees probably, somewhere in that neighborhood. Lower temperature that you'll actually get a reading for the freezing point. Now you have freezing point of the pure substance, freezing point of the solution. Delta T is the difference between those two. Okay? At that point, you have all the data you need. Go back to the theory that we discussed earlier, plug in the numbers, and find out how many moles of benzoic acid that you have, and then divide that into the mass of benzoic acid, and you have the molar mass of benzoic acid. Then all you have to do, as far as calculations go, and remember, calculations is a section of your report that I want to see. The calculation at that point will be, after that, will be determining the error, right? So you need to know what's the accepted value of benzoic acid. I think it's in the hard copy, but if not, I'll put it here. Benzoic acid, the accepted value we're going to use is 122 grams per mole. If you don't believe me, I'll give you the empirical form, the molecular formula. Right? 7 H2 no H6 O2. There you go. Right. And it looks like this. There's the benzene ring, and there's the acid part, benzoic acid. Right. You don't need to know that. You just need to know that formula to calculate the molar mass, the accepted value. If you don't believe me, that's fine. I wouldn't believe me. I'd do it for myself. Okay. So, where are we at? What types of error would we be looking for? Well, this is a good place to differentiate between the types of error. There are 2 types of error in any experiment. One that's not systematic error. Systematic error is the type of error that occurs exactly the same way every time. So if we know what the systematic error is, we can correct for it. Right? One of the questions, post-lab questions, is what if your thermometer, you know that your thermometer reads high every time. Every time you use it, it reads higher than it should. That's a systematic error. And we know how much that is. Let's just make something up. Say it reads high by 2 degrees centigrade. Okay? What effect will that have on the results of this experiment if it reads 2 degree high? Well, think about it. Delta T is equal to final minus initial absolute value. So we're measuring temperature. We're measuring temperature. Final would be the solution. Initial would be the pure substance, right? Subtract the 2. So we measured the temperature, the freezing point here, freezing point here. if this one reads high and this one reads high, what effect does that have on the change? Think about it. It's not that hard. And I'm not going to give you the answer because that's one of your questions. But if you think about it, it's pretty simple. That's a systematic error. Another type of error is random. Random error. Random error is a problem. Because random doesn't means we don't know how much and we don't know what direction. Right? So how do we deal with random error? What could cause random error? Let's see. What could cause random error? Well, from my background, which is working with living systems in agronomy, which is crops and soils, random error is, for instance, if we're conducting experiments out in the field, in a farmer's field, for instance, random error is definitely caused by changes in weather, right? Or over long periods of time, over the growing season, climate change. And I'm not talking about global warming. That's a crock, so don't get me started on that. But variations in seasonal variations can be significant and influence the data that you collect in the field from your experiment. Right? So that's one source of random error. Natural systems just tend to naturally just go like this. Well, how do we correct for it? Well, the accepted way is to repeat the experiment over several years. And that way we get an idea of just how variable the weather has been and in its influence on our results. So the way you correct for random error, since you don't know what it is or how big it is replication. We replicate the experiment, which just means, duplicate means you do it twice. Replicate means 3 or more times. And usually we'll replicate an experiment in the field 4, 5, 6 times to get a good value. If you're conducting an experiment in more controlled environment, like the greenhouse would be a little better. Growth chamber would be even better because you can control the lighting, the temperature variations, day, night. You've got really good control in the growth chamber, but there's still biological variables that you can't account for, right? This plant might be genetically identical, but there's some variability. Right? You just can't do it exactly every time. In chemistry, the variability, the random error, usually comes from unaccounted for sources. Right? You think you've accounted for every possible source of variation so that when you repeat the experiment, then it should give you identical results. But if you have the equipment to measure accurately enough, you will see that no 2 experiments are exactly alike. So there are sources of variation that can never be accounted for. So we deal with that statistically. And this is not the place to do that. But those 2 types of error are always in an experiment. And if you know what the systematic is, good. correct for it. Random error, you just have to accept it, right? And repeat the experiment as many times as necessary to get a handle on what that variation is. Now, just when you in your discussion, your summary and discussion, conclusions in your formal report, you want to make some mention of what possible sources of error there are, and if you redid the experiment, would you make any changes to correct for those sources of error? I want to know that you're thinking. When you do these experiments, you're just not, this is general chemistry. This is not intro to chemistry. This is not paint by numbers. You've got to think. The whole purpose of this lab course is to reinforce the lecture series. And in order to do that, we have to invoke thought in the experiments. So you better think. Otherwise, you're just wasting your time. You're just roboting your way through an experiment. If that's the way you want to go through it, fine. But your grade will reflect it. I want to see some thought. I want to read some thought in your reports. That's why you need to do your report as soon as possible. If you wait till the end of the semester, then you're going to be forced into producing shoddy work. Okay. So there are discussion questions. Let's see. Now let me get your copy. Here. Here's your copy. And you have a pre-lab question. Very first thing right here. And then you have 3 laboratory questions. That's it, 3 laboratory questions. There are some discussion questions. Let me see if they can help us in our understanding. Well, question number 1 is, boiling point elevation and freezing point depression are examples of what type of property? You know what that is, colligative properties. Colligative properties depend on the number of particles of the solute in a solution, not the compound itself, or the character of the compound. Now, here's one we didn't discuss. What quality must a solute have to affect a change in boiling point or freezing point? Well, the most important quality, actually there are 2 qualities. If you want to see a change in freezing point or boiling point, first of all, the solute must be soluble. If you don't form a solution, then you're just wasting your time. But the next most important is it has to be non-volatile. What would happen if we put a solute in a solution, raise the temperature so that we could watch the temperature decrease and solidify? But if the solute is volatile, you raise the temperature, what's going to happen to it? It's going to evaporate, and that will change the concentration. That's a source of error. Fortunately, benzoic acid is not volatile, and neither is lauric acid. So we've met the conditions for that. What's the definition of molality, right? You remember molality? is the number of moles, and there's my abbreviation for moles, per unit mass. So we have moles per kilogram. Moles of solute per kilogram of solvent. Now, why did we choose kilogram? Why was kilogram chosen? Well, here's an interesting connection between molality and molarity. Remember, molarity is moles per liter. Most solutions that we're interested in where we use molarity, the solutions are dissolved in water, right? So how much does a liter of water weigh? A liter of water weighs 1 kilogram. That's the connection. Let's see, what else? What's the molality of a solution that contains 1 mole of non-volatile solute dissolved in 2 kilograms of solvent? There's our definition. Right. It said it has 1 mole of solute and 2 kilograms of solvent. Easy, 0.5 molal. Okay. And number 5 in our discussion questions. I need a whole board for this one. Calculate the freezing point depression of a solution that contains. Oh, calculate the freezing point depression. So we're going to use that same formula. Right? But in this case, we're calculating that value. So that means the problem has to give us this value and that value, or the way to calculate that value. All right, so let's see if it does. Calculate the freezing point depression of a solution that contains 1 mole of non-volatile solute. So we have 1 mole of solute, and the solvent is 0.2 kilograms of water. So the mass is, let's see, mass is, what did I say? 0.2 kilograms of water. And the molal freezing point depression constant, that value for water, is 1.86. That's different than lauric acid. And that's degree C, kilograms per mole. So there we have all our information, and we want to calculate that value. Right? So this just plugs in there, but we have to calculate that one. Right? So moles per mass, we just divide the two, right? And 0.2 into 1 is what? I can do that one in my head. It's 5. Molal. Right? So 5 molal and 1.86 degrees C per molal. So we can cancel the molals. Leaves us with degree C. So 5 times 1.86 is what? Yeah. I don't want to do that one in my head. 9.3. 9.3 degrees C, and that's equal to the change in temperature. Now, if this is freezing point depression, which way did the temperature change? from the pure substance to the solution, the temperature went down for freezing point from pure to solution by 9.3 degrees. That's a lot. But it's not something that doesn't happen, right? How do we make ice cream? We mix salt in water. And when we mix salt, well, actually salt in ice, we mix salt in ice, and it depresses the freezing point. So the temperature of the ice water solution drops. As long as we've got ice and water together, and the water has salt in it, we depress the freezing point of water below 0 degrees centigrade. In fact, we want to get it cold enough so that the freezing point is lower than the freezing point of the custard in our churn. Right? That's when it freezes, and that's when it becomes edible. Okay, I think that's all of our discussion questions. Let me make just a quick check. All right, so you have one pre-lab question, and you have 3 post-lab questions. All right, I gave you a hint for the first post-lab question. Read it, and you'll see it. The second post-lab question is, why is molality used instead of molarity when doing colligative property studies? I gave you that at the very beginning. Why do we use molality instead of molarity? Right? Think. Number 3, what are some possible sources of error in this experiment? So I thought of 4 here, but those are not the only ones. Right? So if you give me one that's not on my list and it's reasonable, sure, I'll accept it. Just think about possible sources of error. Step by step, you're doing something. You have to weigh something out, right? Don't tell me that you've never weighed anything out and not spilled something. Right? Sometimes you know it, sometimes you don't. What about the solute and solvent? Are you just assuming that they're pure? How about reading your thermometer? You know what I'll explain this one. When you're reading a piece of glassware in the lab, could be a thermometer, could be a burette, right? It has markings on it, right? Like we did with our burette, right? It comes down to here, here. Has a valve on it, and then a spout. Where is your eye supposed to be? Remember, when we were using the burette, what did I tell you? The eye has to be level. That's why you have these, periodically, you have those marks that are all the way around. If you look at your burette and you see 2 lines at that point, that means you're not level with it. Because front to back, one should be covering the other. If you're looking at it up here, you're seeing both lines, front and back, right? So your eye needs to be here, right, level. What if it's not? What if you look like your eye's up here? What are you seeing? You're seeing that line, you're seeing that line. This has a special name. It's called parallax error. Right? Parallax. Parallax is an astronomical term. And it's used, a measurement of parallax is used to measure the distance from the Earth to some heavenly body. Now, it can't be a long way off because parallax only works close by. But we can use parallax to measure the distance to a very near stars, or to a planet or an asteroid or something like that. Actually, it works best with stars because, generally speaking, stars don't move. You know, they're fixed position in the sky. If you're trying to measure the distance to a comet or a planet, they're always moving. In fact, the word planeta is Latin for wanderer. So planets were known as wanderers in the beginning. But this parallax error is due to a difference, an angular difference in viewing. So if you view your thermometer and you're not level with it, you're introducing an error. Okay. So I've given you enough hints, and actually some of them actually answers to the questions, if you were listening. So what you need to do now is take that information and generate a report as if you were there. Good luck.